So 8.2, we're talking about series. It's the same thing as infinite series. For example, the series from n equals 1 to infinity of 1. So now we still have a bunch of terms, but we're going to have a plus sign if we're adding them up, right? So this is trivial, of course, right? And then of course we're going to be talking about, does this one converge or diverge? Of course it diverges, right? If I add any single number up an infinite number of times, right? It's except for 0, right? It's going to diverge. So we should recognize, understand that a series is it's just like a sequence, but we're summing, right? So like there's a really famous one. Well, I showed you the series for e to the x already, right? That's and this week I will show you how it's developed. Okay, but there's a real famous series here, the series from n equals 1 to infinity of 1 over 2 to the n. This one actually adds up to 1. But let's write out some terms here, because this is the thing I'm telling you we need to be able to do. We need to be able to write out terms. If you don't write out terms, you might not be able to think about what's going on. So obviously it's 1/2. This is a geometric series. I'm multiplying by 1/2 every time, so I've got 1/2 plus 1/4 plus 1/8 plus 1/16, right? Plus etc. And it's kind of crazy to think that this thing adds up to 1, but it does. I'm going to show you a couple of ways that it does. This is an old mathematician's joke. A mathematician can only afford 1 beer, but he goes into a bar and orders an infinite number of beers. But he just asks the bartender to pour it half a glass first, and then a quarter of a glass, and then it all only adds up to 1, right? So sad story that the mathematician can't afford more than 1 beer, and you've got to put the math joke in there too. So I'm going to start with a square of a 1 by 1 square, right? So here's my 1 by 1 square, right? And I'm going to cut it in half. So now here I have a piece that's a half. There's that first integer. And when we're adding these integers up, we're really kind of thinking of them as areas, and I'll show you what I mean by that in a second. But now I'm going to cut this other part of the square in half again, right? And so now what's this bottom corner piece? That's a quarter of the square. And then cut the next part again in half, and now what's this next piece? It's an eighth of the square. So you can see if I keep doing this, eventually I'm going to run out of room, right? If I do it infinitely, eventually it's like cutting the paper in half and cut it in half and cut it in half, right? Eventually the scissors are going to be too big for the piece of paper you have left, right? But obviously the piece of paper here is a total of 1, right? The area of 1. This is kind of an interesting comparison to what we're going to do with one of our tests, the ratio test. So at 1, I had a height of 1/2, right? And then at 2, I had a height of 1/4. And at 3, I had a height of 1/8. And you can see the width of each of these, right? These areas are matching up here. This is the same area as here. And you can see the integral, you can see the function, right? You can see the function kind of, right? The area under the curve of the function is more than the area I get from the sequence. And so this is one of our little tricks that we're going to do later for convergence. If I could do that improper integral and I get a convergence, then of course the series will also converge. So the first way that we find out if a series converges or not, okay, is we start with partial sums. We turn the sum into a sequence of partial sums. Okay, so the first term sum, the first two terms sum, the first three terms sum, the first four terms sum, and if that particular sequence has a limit, and we can find a limit, then that turns out to be the sum of our series. And I mean, we're not proving any of this to you in the class. And Adrian and Charlie, as juniors at university, you'll be proving all of this stuff in some class 2 semesters called Advanced Calculus 1, Advanced Calculus 2. So we don't care. The rest of us don't care about the proof. But there are out there if you want to look at them. But the first thing we want to ask is, does this series converge, right? And then how can we show series converge or don't converge? And so in this particular case, we're going to find our partial sums. And I'll have you do one like this in WebAssign. So what's my first sum? What's S sub 1? If I add up my very first term in this particular piece, and I'm using this one, right? I'm using this famous mathematician by Zabir. So what's my very first sum? It's just 1/2, right? And what's my second sum? I'm going to add up the two terms now. 1/2 plus 1/4, right? And what is that? What is my second sum?
3/4.
3/4. And so then I'm asking, what is my third sum? So it's 1/2 plus 1/4 plus 1/8. So that's 3/4 plus 1/8, right? And that's what, 3/4 plus 5/8, right? Sorry, 3/4 plus, no. Help me. 7 over 8, right?
See, there's a pattern happening.
Yes, exactly. So you can see this pattern happening already, and in fact, we know this is going to converge, right? We know this particular one is going to converge. We can already see, but what we would like to be able to do is come up with an nth term for this particular series, right? Come up with an nth term for this particular series. So we would like to be able to find S sub n and then look at that limit, right? So what do you think here? What do you got for me?
N over n plus 1?
Almost.
Almost.
Yeah,
Okay.
yeah. That would be nice if it was. Definitely, right? We see it's a limit of 1. That's what we want. But I don't think I'm getting that from my second term. When I plug in 2, I get 2 over 3. Right? When I plug in my second term here, when I find S sub 2, I'm just plugging in 2 for every n, and I get a 2 over 3. I don't get a 3 over 4. So anyone else got one for me? The downstairs is pretty easy, right? What's happening downstairs?
Is it just n, 1 over n?
Not 1 over n, because right, even on the first one, that one fails. For S sub 1, I'd get 1 over 1. But the downstairs...
Isn't it 2 to the n minus 1 over 2 to the n?
There it is. So downstairs is pretty easy to see 2 to the n, right? So I've got a 2 and then a 4, then an 8. I've got powers of 2. And upstairs is always one less. So I've got 2 to the n minus 1 there, right? And so then obviously I'm going to divide and conquer. I've got 2 to the n over 2 to the n minus 1 over 2 to the n. So I've got 1 minus 1 over 2 to the n. Is everybody with me? Don't let me go too fast. Hey, everybody's here. Everybody's here. Adam. Adam woke up. Morning, Adam. I just started. I did some homework from 8.1. I did some homework questions, and I'm just starting 8.2 right now.
Okay.
So what's this limit, right? The limit as n goes to infinity of s sub n is what? The limit as n goes to infinity of 1 minus 1 over 2 to the n. And obviously that last piece goes to 0. 1 over 2, 1 over 4, 1 over a quadrillion, 1 over a godzillion eventually becomes 0, right? So this equals 1 plus 0, which is just 1. And we already knew that thing geometrically, we could see that it added up to 1. So this is a first way of trying to find whether a series converges or not, right? And to find the sum. So I take my series, I create a sequence of partial sums. I come up with the nth term of the sequence of partial sums. If that limit exists, then that is the sum of my series. That limit is the sum of the series. If that limit doesn't exist, the series diverges. But remember, I might be able to show that there is a limit, but not find the limit, right, by using this monotonic and bounded piece. So pretty interesting, these partial sums. So I'm going to put one homework with partial sums in there. In the web.
Can you explain that again?
Yep.
The partial sums you're using to find the nth term?
The nth sum. Right. So remember I'm adding up 1/2 plus 1/4 plus 1/8 plus 1/16. And if I could get all the way to the end, I would have the sum. So what I'm doing is creating a sequence of those sums until I get to the last sum. And the last sum is the sum of everything. Right? And so, again, we'll be connecting that to that integral to infinity kind of thing. Right? So now, right, we have a series. Let's just recap it and say it one more time. We have our series. Our series is here, okay? We don't know the sum yet. Well, I showed you twice what it is, right? So we have the series, and then we create the partial sums. So we create the first partial sum. But again, look at my series. The series is n equals 1 to infinity of 1 over 2 to the n, right? And that's 1/2 plus 1/4 plus 1/8. And so what I'm going to do is create the first sum, and then the second sum, and then the third sum, and then the fourth sum. So add up the first term, add up the first 2 terms, add up the first 3 terms, add up the first 4 terms. And now I create a sequence of partial sums, right? So S sub n is now 1/2, comma, 3/4, comma, 7/8, comma, dot, dot, dot. I would like to be able to figure out that last an nth term for the partial sums, and we did it, right? So we got that particular, we got an nth term for that sequence, and we already know now from 8.1 how to find out if the sequence converges. It just so happens to turn out that if the sequence converges to some number, that happens to be the sum. And that makes sense because remember, this thing is the sum at the end. So if we find the limit, we found the sum. How is that, Eleanor? Is that okay?
Yeah. So the series is the sum of sequences?
It's other way, sequence of the sums, and the very last one in it, right? So look with so here's my sequence, right? The first one is the first sum. So the first part of the sequence, the first term of the sequence is the first sum. What's the next term of the sequence? It's the second sum. It's adding up the first two terms. So that very last term, right, which we figured out is 2 to the n minus 1 all over 2 to the n, that one is the sum. So the limit of the sequence is the sum of the series. Let me write it. The limit of the sequence of partial sums is, if it exists, right, is the sum of the series. It's a little confusing. You got to get in there and write. You got to get in there and write out terms and try things. I do believe the TI-83 will give you sums, right? So just Google TI-83, 84, series, and it should be able to give you some, so you can double check things, right?
It's just too many S's.
I understand. Sequence, series, partial sums, right? So the sum, I get it. So let's look at the sum of a geometric series. The one that we just looked at is a geometric series, right? It's 1/2 times 1/2 times 1/2 times 1/2, right? But we want to be able to write our geometric series from I'll use I equals 1 to infinity of a sub 1 times r to the n minus 1. And r is that common ratio, right? Or that thing I'm multiplying by, right? So I take any previous term, I take a sub n and divide by a sub 1. Sorry, a sub n divided by n minus 1, and I'm going to get the ratio r. I take any term, divide by the previous term, I'm going to get that common multiple, right? That ratio, right? Like, for example, we had the series from n equals 1 to infinity of 1/2 to the n, right? And remember, I'm going to factor out that half. For geometric, I want to factor out that half, and you'll see why. And we already know what this one is. So 1/2 plus 1/4 plus 1/8 plus 1/16, and you can see obviously if I'm multiplying by 1/2 each time. That's my common ratio, right? Everybody with me? So if I took 1/4 and divided by 1/2, I would get 1/2, that common ratio. If I took 1/8 and divided by 1/4, I get the common ratio, 1/2. Any consecutive terms will get me that common ratio. And then a sub 1 is obviously the first term. Actually, I don't need that. I don't need that. I'm sorry. I don't need the one a sub 1. Just a. Sorry. Because you can see I've got that factor of 1/2 there every time, right? It's 1/2 times when n is 1. It's 1/2 times whatever I get when n is 2. It's 1/2 times. So that thing's going to be repeated over and over. So if I write this one out, I get a times r sub 0 plus a times r sub 1 plus a times r sub 2. Sorry, r to the 2 plus dot dot dot, right? Again, rewrite. I get a plus ar plus ar squared plus ar cubed, etc. Right? So pretty easy to see what that geometric series looks like. There's a fact, like in mine, down at the bottom of my screen, there's a factor of 1/2 in everything, right? And in this box, there's a factor of a in everything. It turns out that if the radius r, okay, that common multiple is in absolute value less than or equal to less than 1. So if absolute value of r is less than 1, right, which is what, from -1 to r to 1, right? That's what that absolute value means, right? It's a radius, right? So from the origin to +1 or from the origin to -1, right? Like a circle, right? So my radius here, right, is +1. And then my radius over to this way goes to -1, right? That's what that absolute value is doing for us, right? It's giving us the direction, that same distance in, you know, if I'm on the x-axis, to the right and to the left. So if the radius is in absolute value is less than 1, then the series from I equals 1 to infinity, damn it, and I want to end there. I know I'm going to confuse everybody, I'm sorry. From n equals 1 to infinity of a to the a times r to the n minus 1 is equal to a over 1 minus r. And this is a crazy result. Crazy result. And it's easily proven. Easily proven. So if I recognize that I have a geometric series, right? So the partial sums would work whether it's a geometric series or not. Sometimes it doesn't work. But so if I have a geometric series, I've got another thing to try. I can look and see if this ratio is less than 1, and then I can plug into this formula, which we're going to prove to you. Okay. So let's take one that we already know the sum of. That is geometric, and that's the one we just had, right? So we had the sum of n equals 1 to infinity of 1 over 2 to the n. We're going to rewrite that as our geometric piece. Yes, and we've done it a couple times. I'm factoring out a 1/2. If I factor out a 1/2, now my power is to the n minus 1 power, and that's what I want. You can see I've got a match here of my first term is 1/2. My radius is 1/2. And my power is matching to the n minus 1, right? And so now I can go right into the sum. So what's the upstairs? What's that blue piece is 1/2. That's my first factor, my term, right? My same factor in every piece of the sum. And then I've got a 1 minus r, and my radius is 1/2. So I've got 1/2 over 1/2, which again is 1. And there's the sum, but we knew the sum was 1.
And is it only a geometric series when there is a ratio?
Exactly. Exactly. I need that. I need the terms to be being created by multiplying by the same thing every time. Arithmetic, I'm adding the same thing every time. Geometric, I'm multiplying by the same thing every time.
And if R is greater than 1, does that just mean it's divergent every single time?
Divergent every time. Yep. And like, for example, let's just create one, right? Let's create one. So for example, let's just make the first term 1, right? And then let's do powers of 2 to the n minus 1, right? So I've got from n equals 1 to infinity. And obviously this is 1 plus 2 plus 4 plus 8 plus 16. It's pretty obvious. I mean, it would be kind of nice to have this kind of money pretty quickly, right? Oh, today I get $32. Next, say $64, right? 128. That's pretty good a day. But you're going to be pretty rich pretty fast if you keep doubling, you know, the amount of money you're taking in every day. Yeah, so if the radius is bigger than 1, it diverges. That particular proof is pretty simple. It's on page 566. It's really a simple proof. I just take a couple of things from my sum and put them together, and then I guess I should show it. You don't have to copy this, okay? You don't have to copy it. So I already know I can come up with a partial sum, right? So my series from n equals 1 to infinity of a to the r, a times r to the n minus 1 is a plus a times r plus a times r squared, right? I'm going to keep multiplying by r every time. So I can find an nth partial sum here, right? I can find an nth partial sum easily, right? So it's wherever I want to stop is where I'm going to stop, right? So r squared up to you know, what could I think of as, what would I want to kind of think of, where would I end this? Well, if I'm going to infinity eventually, right, I'm going to get to some number like 100, and I'm certainly going to get to the one before that, right? So like 99. And so I certainly am going to get up to a times r to the n minus 1 eventually, and then I can keep going. But it doesn't bother me that much, right? I know I can get to anywhere, right? A times r to the billion power, right? So, but in particular, I want to go there and then multiply this by r. So I want to take that partial sum that I got and multiply by r. Now, how do I start? I start at a sub r plus a sub r squared. Plus a times r cubed, right? And then what happens to my very last term there? What does that become what happens to when I multiply that very last term in blue here? Multiply my very last term by r, what happens to the power? R to the what?
N.
R to the n. And the one right before it is plus a times r to the n minus 1. Right? So I'm saying I'm stopping there for my partial sums. And then what am I going to do with those two things? I'm going to subtract them. I'm going to take these two and subtract them. Okay. So I'm going to take S sub n minus r times S sub n. And I'm going to look at them kind of term by term here, right? I'm going to subtract these two, and subtract these two, and subtract these two, and subtract these two. So what am I left with at the end? If you see those diagonals that I'm subtracting, they go away, right? They match. So what am I left with? I'm left with a minus a r sub n. Right? Do you see the a sub, right? A times r's cancel. A times r squareds cancel. So I'm left with the first term and the last term. This is something called a telescoping series. So I'm left with the first term times the last term. I'm going to factor out an S sub n over here. So I get 1 minus r equals a minus a times r to the n. And then I get my partial sum, which is a minus a r to the n over 1 minus r. And again, I can factor out an a there. And now what do I want to happen? Once I've got my term for my nth partial sum, what do I want to do? I want to see what happens at my limit, right? And it's pretty obvious, right, that if r is less than 1, 1 minus r to the n goes to 1, right? R to the n is going to go to 0, right? And if r is bigger than 1, it's going to go to infinity. If the absolute value of r is greater than 1, 1 minus r to the n is going to go to infinity. So obviously I want the blue version, right? I want this to go to 1, and now look at what's left. So that nth sum is 1a over 1 minus r, which is what we had before. Did you go out, Lucy? Lucy, did you go out for a walk? Okay. So it's kind of cool, but you're going to use that geometric series sum piece in a bunch of the homework. So we're going to talk briefly about the power series here. So this is our first power series. And it turns out to be the sum of n equals 0 to infinity of x to the n. And I need you to remember that x to the 0 is allowed. All of a sudden it's allowed. We've been saying to you forever, right, that x to the 0 is 1 provided x does not equal 0, right? So 0 to the 0 is one of these indeterminate forms, right, that we dealt with with L'Hopital's rule. So, but now, once we're in this particular place, we want to allow you to have a 0 to the 0 as 1. So we're saying x to the 0 is allowed to be 1 now. So x to the 0 is 1. Let's write out some terms here and see what this particular series. So this was our old school thinking, but you're in calculus now. You can handle x to the 0 now. And so let's write out some terms for me. Anybody got the first term?
X to the 0.
Thank you. It is that easy. And then plus?
X.
Yep. Plus x squared, plus x cubed, plus dot, dot, dot forever. Right? And so, of course, that can be rewritten as 1 plus x squared, plus x cubed, plus dot, dot, dot. And you can see why it's called a power series, because it's the power of x is just increasing, right? It's also kind of geometric, right? It's very geometric. I can see I'm multiplying by x every time, right? And if I want this particular thing to converge, what kind of x's should I be able to plug into it? What values of x's can I plug into this and it'll add up?
Less than 1.
Less than 1 in absolute value. So negative 1/2 positive, or positive 1/2, right? 1/3, 1 over pi, right? Any number in absolute value that is less than 1 will converge. So if it did converge, I now have n equals 0 to infinity of x to the n. It's a little bit strange that I'm not writing it as an n minus 1 power. It's also a little strange of what this thing is on my screen. Some news thing. But what's my first term is 1. And what's my radius? What's my radius? What am I multiplying by every time?
X.
Nice. And guess what? We're going back to pre-cal, to long division here, right? We're gonna take the 1 minus x and we're gonna divide into 1. I know this is painful for some of you. How many of you are haters of the long division? How about haters of the synthetic? Oh, you don't want to tell me the truth about it. Okay, Angel, thank you. I'm not going to let them know I'm a hater. So I'm dividing 1 into 1. How many times does it go in? It goes in once, right? And then I'm going to come back and multiply, so I get 1 minus x. And then I'm going to change my signs and add, right? Change my signs and add. If I'm going too fast, let me know. So where did I get that first red 1 from on top? I'm saying 1 divided into 1. That's 1. Okay. Come back and multiply. So the red times the black will give me the highlighted red, right? The red times the black gives me the highlighted red, but then I change my signs and add, like we did long division in, I think it was 4th grade. I think it was 4th grade I was doing long division. I don't remember. Sister Salvatore was my teacher. She was the only nun that didn't beat me. And then rinse and repeat. Oh, so subtract. So what do I get? I come down to x, right? And now rinse and repeat. So now 1 into x. How many times does that go? What's x? And then come back and multiply. So I get x times x minus x squared. And then change my signs and add. Change my signs and add. The first term always goes away. And then I get an x squared. And so you can see this long division is giving me the same exact series. So this is my power series. This is my very first power series. We're going to use this a lot tomorrow. So this first power series is definitely going to be on our formula sheet, right? And we have we have, the sum of n equals 0 to infinity of x to the n is 1 over 1 minus x. And you see I'm putting the x's in parentheses, and I'm doing that for a reason, which is 1 plus x to the 1 plus x to the 2 plus dot, 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 right? And more importantly, our absolute value of x has got to be less than 1. So this particular box is going to be used for us to create power series. I'd like to try and start one today, but on every final exam I say to you, create the following power series, right? And then find me the radius of convergence. And so for this particular power series, we've got it, and you can see I've got parentheses around my x. That's for later. And I guess I should put parentheses here too. And what's my radius of convergence here? What's my radius here? Yes, David said it. Eleanor thought it. Charlie gave me the finger. He actually gave me this finger though, and that's correct also. 1. The radius is 1.
Yeah.
Right? So, and where are we getting from that? We're getting that from the geometric series, right? We know this thing is going to converge if our radius is 1. Now, the weird thing is, does it converge at 1 or at -1, right? That's the weird part about it. Does this particular thing converge at 1 or at -1, right? So, and that's what we're coming up to pretty soon. So the radius of convergence r equals 1, right? But remember what I'm saying there is the absolute value of x is less than 1, right? But the radius is 1. Now, the interval of convergence, which I don't spend a lot of time on, just because I don't care so much. I just want to know, does it converge? But what radius does it converge? So my interval of convergence could be -1 to 1, -1 and to 1 inclusive, or -1 inclusive to 1, or inclusive at -1 and 1. And so how do you find out if things are convergent at the endpoints of your radius? Is you have to plug them in and then go back and do one of our tests. It might be partial sums, right? It might be some other test that we're going to show you. Okay. So go ahead.
Are the radius of convergence and the ratio related?
Yes, exactly.
Is it the same?
Yes, because remember we needed that ratio, right?
Because the ratio was x.
Exactly. The ratio has to be less than 1. It is the radius. The ratio is the radius, and we use r for exactly that reason. We're using r.
So the radius is just like the maximum value of the ratio for it to converge?
Yeah, so the ratio, remember, you're multiplying every term by that same number, right? That's the ratio.
Mm-hmm.
And that's what we're calling is our radius as well. It is our radius. So if I'm multiplying by 1/2 every time, right? My ratio is 1/2. And that particular value fits inside of my radius of 1. So I have convergence. Yeah. Yeah, I get it. I get what you're saying. So, but you see what I'm saying here is I care about how far, how big is the circle? How far on the curve? Remember how I said I had that curve covering the other piece of the curve on last class? That's kind of where this ratio is. And then what about at the endpoints? it always looked a little iffy right at the endpoints. Remember when I was putting those curves on top of each other? Right at the endpoint of that radius of convergence of 1, did the positive one cover? Did the negative one cover? That's what we're questioning, and that's where the interval of convergence comes in. So don't let this panic you. All I need you to know is right now is this power series box. This is going to be your guide to creating power series. And this all came from the geometric, right? Which is what we're talking about in 8.2 here. I want to look at the telescoping.
I have a question.
Yes, Charlie.
Yeah, in the book it says that if the ratio is greater or equal to 1, it goes to divergence.
Yes, if that ratio is bigger than 1, right? And I showed you one, right? I showed you a radius of 2, right? I had that series of 1 times 2 to the n minus 1, which was 1 plus 2 plus 4 plus 8 plus 16. That's a lot. It's getting to be a lot of money really quickly. Yes, divergent. If the radius is...
Yeah, but it's inclusive. 1 is inclusive in there. It says greater or equal to 1. So if it is equal to 1, so our interval...
I agree. I agree for the geometric. I agree. So, for example, if I had a radius of 1, right? Now I get 1 plus 1 plus 1 plus 1 forever, right?
Mm-hmm.
Divergent. What if I have a radius of negative 1? That one's kind of tricky. So when n is 1, 1 minus 1 is 0, so positive. So I'm going to start with a positive and then a negative. So positive, negative, positive, negative, positive, negative. What about this one? What are you thinking there? Divergent or convergent? This one's
right?
divergent, right? By oscillating.
Oh, yeah.
It's 1, then it's 0, then it's 1, then it's 0, then it's 1, then it's 0, right? So divergent as well. I can't get a sum out of it, right? I don't know if the sum is 1 or 0, right? So divergent. If I can get a sum, like 7, convergent. If it's infinite, divergent. If it's oscillating, divergent. Right? We had one other limit where it was different from the left and right, where there was a gap, but that doesn't happen in this in our case. This one is kind of there's kind of a gap here, right? I'm always going from 1 to 0 to 1 to 0, so there's kind of a jump. But I would call it oscillating more than I would call it a jump. So I agree with Charlie, though. This interval of convergence is going to come into play. We're going to have a radius of convergence for all our series. And then we could also have an interval of convergence. If it's geometric, it's going to be this one always. If it's geometric, it's that one. For geometric, I'll never include the endpoints. Good point, Charlie. Thank you. All right, let's look at a telescoping. How are we doing here today? I know it's confusing. I know if you haven't seen it before, it's like, what the hell's going on? And you're going through exactly what I went through, and it's just about sitting down with some paper and writing things out. If you watch me play guitar, you're not going to be able to play guitar. If you watch me parallel park, you're not going to be able to parallel park. You have to get in there and write and do it. And you know, there's lots of examples in the books that you can do. Paul's notes, lots of examples. You know, you can just go on YouTube and Google the sum of a geometric series, and you'll see lots of nerds on there doing the same thing. I think it's enough for you just to do the examples in the book over. So actually, before the homework problems, do the examples. The examples have the work written out. And they skip some steps, so don't skip the steps. Make sure you understand everything step to step. And then do the WebAssign, okay? Because am I putting a partial sum on your test? No. Am I putting a geometric series on your test? No. Am I putting a power series on your test? Yes. We're going to start that maybe today, for sure tomorrow. Am I putting a Maclaurin series on your test? Yes. You don't even know what it is yet. And then I'm putting a couple of the convergence tests on your final exam as well. Okay. So even though this stuff is confusing and boring and lots of writing and the terminology sucks, just don't stress about it. Okay. Just read and take it in. Right. All right, I want to do a telescoping. Because you might notice something in the telescoping series. So have you all, I don't know, what grade was it? We went to some stupid museum as a class trip, and you had to look at the old telescopes, and they expand out, you know what I'm saying? And then you push them back together, and you're left with the beginning and the end. So we already kind of saw a telescope happen today, where I subtracted these two pieces and all those diagonal things went away. So I'm going to look at this particular series, the series from n equals 1 to infinity of 1 over n times n plus 1. Do you recognize anything about this? This particular series, does it look like anything we've seen already this semester? You can't use the Monday excuse. You can't use the Monday. You really should not be using the I'm still mad at you for the midterm exam. You really should not be using that. You should be over that already. So why the hell isn't anybody talking to me? What do you think here? Have you seen this before? Say yes. Just say yes. Okay. Eleanor's shaking her head. Oh, thank you. Who said that?
Is it the,
Nice, Ash. Thanks. Go ahead, David.
okay. No, I lost it. I was thinking partial fractions.
That's it.
But I
That's
think
it.
I'm way off.
That's it.
Oh, it is.
It is.
Okay.
Yes. Yes. Go team. Go team. Who else had partial fractions on their mind? Damn it. You should lie to me a little bit. If I say to my girlfriend, do you love me? And there's any hesitation, right? Or an answer like no, it's over, right? So you gotta fake it till you make it. I say, just tell me you love me until you eventually maybe you'll love me again. So yeah, this is partial fractions. Partial fractions. So we want to manipulate this into an a over n plus b over n plus 1, right? So we want to turn this into 1 over n times n plus 1 into a over n plus b over n plus 1. So telescoping series is a nice way for me to go back to partial fractions for you if you had trouble on that partial fractions problem, right, for the final. Anybody have it done for me yet? I think I get b is minus 1 and a is 1, right? Anybody else get that? %, attendance today. That's awesome. Thank you for all being here. Oh, less than 2 weeks left, and then hopefully you have some time off. I got another 2-week long class starting the week after we're done. But hopefully you have a little bit of a break. Anybody else get the same coefficients? Thank you, Eleanor.
I
David,
did.
thank you. Thank you, Ash. So what do you want to do here? What's your instinct? So remember, what we're kind of asking is, what are we even asking? Angel Good, what are we even asking here? Does this particular series do what?
Converges.
Converge. Does it converge? Exactly. Does it converge? And so, and if so, can we find where it converges to, right? If it does converge, where does it converge to? So what have I been telling you to do all the time here? Write down some terms, right? So it turns out if I write out terms in this format, I don't see the pattern as well. And you certainly could write out terms there and see if you can do this, but it's a little bit easier in this case because you're going to see things go away quickly. So I want to write out terms and then start thinking about partial sums, right? So I want to start writing out some terms and then I'll start thinking about partial sums. So so when n is 1, what do I get? I get 1 minus 1/2. Do you agree? Yes, you agree with that. When n is 2, okay, I'm going to put that underneath. Okay, I'm going to put it underneath. When I first would do this, I wouldn't know I would put it underneath, but because it's hinting at me that it's telescoping, that when I close it, pieces will collapse. Interior pieces will collapse, and I'll be left with the beginning and the end, right? So, but when I put in n is 2, do you see what I get? I get 1/2 minus 1/3. And look at that. Look at the first partial sum. I get the first term and the last term. And look at my second partial sum. I get my first term and my last term again. Do you see what I'm saying? My first partial sum, and I'll erase this in a second, I get the first term and the last term. That's my first partial sum, just the first term, right? In my second partial sum, the 1/2 will cancel, so I get my first term and my last term again. And this is the essence of telescoping. And it gets complicated. It might give you the first 2 or 3 terms and the last 2 or 3 terms as well. But let's do the next partial sum. Let's do the next term. Let's just do the next term. But remember, we're adding these things together, right? So what's the next term? When I start with n is 3, I get 1/3 minus 1/4. And now, again, if I look at my partial sum, I get the first term and the last term. So I'm thinking this is going to happen. I'm pretty convinced now, right? Aren't you? That all those middle terms are going to cancel out. So that here's the problem. I want to write out the last 2 terms in terms of n. So that's where it gets a little bit confusing, right? I want to try and write out the last 2 terms in terms of n. So imagine my last term is n, right? Imagine my last term is n. So I've got that already. I've got 1 over n minus 1 over n plus 1, right? Can you see that very last term? When n is n, remember I'm doing an nth partial term. So when n is n, I get exactly what I have there. But what about the one before it? What is the value of n right before it? So at the end I had n is n, right? What's the one right before it? So if n was 10 at the end, what's the one right before it? 9. Or n minus 1, n minus 1. So I'm going to replace every n with an n minus 1. And so look what happens, right? So I replace this n with an n minus 1. I replace this n with an n minus 1. And so what happens here, I get just the 1 over n here, right? And I know these two are going to cancel, and 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 these two are going to cancel. And now I have my partial sum. S sub n is 1 minus 1 over n plus 1. There's my partial sum, telescoping. Grab the first piece, everything in the middle dropped, grab the last piece. Now, what am I interested in doing with this? I'm interested in taking the limit of a part, right? So I've learned that if I have a series and I create a sequence of partial sums and I can find the limit of the partial sums, if I can find that limit, that means the series converges and the series converges to that limit. And so what is this limit? What is the limit as n goes to infinity of S sub n? It's the limit as n goes to infinity of 1 minus 1 over n plus 1, which of course is 1 minus 0 is 1. Right? 1 over n plus 1 goes to 0, right? And so there I have it. So I know now the series from n equals 1 to infinity of 1 over n times n plus 1 is equal to 1.
Why did you need the second to last term? I don't see what you did with it.
I wanted to show, I wanted you to see that those two match up and cancel. And it should have been a minus in between there. I wanted you to see that, you know, because I saw that these canceled and these canceled. I wanted to be able to go the other way and show that things canceled in the middle. And I'm only left with the first term and the last term. If I didn't write out that second to last term, Eleanor, do you see that I'm not so convinced that 1 over n will go away? If I didn't write out that second to last term, I'm not that convinced. I don't see from this pattern that I will definitely get that one to cancel. I mean, maybe I do, but I wanted you to see that I would get the 1 over n minus 1 minus the 1 over n, and then those two would cancel.
How free are you to like move constants around like in that? Like say I had, instead of the beginning it was 6 over n plus n over 1, where I could just do away with that and make it a lot easier.
Exactly. Yeah, I see what you're saying. Yeah, you'll have, if you do the one I give you on WebAssign, I think there'll be 2 terms left at the beginning and end. So you can't be too anxious to have things cancel. Just start writing out terms and then see if you see a pattern. And then you can rearrange things any way you want so that it will obvious these are going away and these are going away and these are, you know what I mean? So yeah, feel free to write it out once the super, sequences for dummies, you know what I mean? Put it in there without simplifying anything. And then rewrite it simplified, and then rearrange so that you can see what's going to go away and what's not going to go away, right? So it takes a lot of writing at first, okay? But yes, you can manipulate things any way you see fit to see if a pattern shows up. What else do I want to do today? guess I want to talk about this test for divergence, and then I'm going to do a power series. Okay. So we've found a couple of ways to find if a series, right, when you're adding, you're summing, if a series converges. Partial sums, geometric, right, that type of thing. But it's often easier to show it doesn't converge, and so that's why we have this test for divergence. So if you do the test for divergence first, right, then you don't have to go bother with partial sums. If you're convinced that it diverges, you can stop there. Does that make sense? So the key about this is if I'm going to eventually get to a sum, what do I have to start adding? If I'm going to get somewhere finite, my terms had better start turning into what? If I'm going to get a sum, David, give everyone else a chance to think here. If I'm going to add up a bunch of numbers, right? And the numbers, you've seen the numbers, 1 over 8, 1 over 16, 1 over 32, 2, 4, 6, 8, you know. If I'm adding a bunch of numbers and I'm going to get a sum, I had better eventually start adding what kind of numbers? David, you can, if you've got an answer, that's fine with me. Eleanor, if you've got an answer, that's fine with me. Anyone else has an answer for me? What do you think? What do I have to start adding eventually in order to get a finite answer? Eleanor?
Really small numbers.
Exactly. So if I have a series that has a limit of 0, right? I've got this potential for convergence. If I have a series that I'm eventually adding things so close to 0 they might as well be 0, it's quite possible I've got something convergent. So my test for divergency is, if I have a series that doesn't have a limit of 0, okay, so any number, so I've got some other number as my limit, right? So for example, I have an answer of 1/3. So my limit at the end is I'm adding a bunch of 1/3 for how long? Forever. If I'm adding a 1/3 forever, I'm never going to converge, right? 3 times that 3 of the 1/3 is going to be a 1. So now I'm adding a bunch of 1s at the end, right? So there's my test for divergency. It's that simple. So here it is, test for divergence. And this is kind of our first of many tests in chapter 8. But I'm going to go away from the test after this one, just because it's the only one in 8.2. I don't want to have to go back to 8.2 to talk about this particular test. If the limit of my, so I've got a series from n equals 1 to infinity of a sub n, right? And if the limit as n goes to infinity of a sub n does not exist or is infinite, right? Or it does not equal 0, so that the limit goes to a billion. Now I'm adding a billion a bunch of times. The limit doesn't go to 0. I am not adding nothing anymore. I'm still adding something. And if I keep adding something, no matter how small it is, if it's not 0, I'm gonna diverge. Then the series from n equals 1 to infinity of a sub n diverges. So it's often nice just to do that limit right away before you go and try and do this horrible partial sums thing, right? If you jump right to partial sums, this thing could turn into such a mess, right? So let's look at the sum from n equals 1 to infinity of n over n plus 1. Right? So does that series converge or diverge? Right? That's what we're asking. Does that particular series converge or diverge? So let's do what we're not supposed to do. Let's just jump right. Now, look, if I see that it's geometric, hey, I know what to do, right? If I see it's possibly telescoping, like looks like partial fractions, I know what to do. If I don't see that, then maybe I should just check and see if it's divergent first. Because if it's divergent, I don't have to do anything. But let's pretend I don't realize I could check for divergence first. Let's pretend that I'm just going to go to partial sums, right? And so how would I do that? I would start writing out. When n is 1, I get what? 1/2? When n is 2, I get 2/3? Yes? When n is 3, I get 3/4. It's pretty easy to see the terms, right? I don't really have to plug in anymore. 4/5, 5/6, right? What is that number going to? What is the next number getting closer and closer to?
1.
1. So eventually, I'm still going to be adding something really close. I'm going to be adding 0.9999 and then 0.9999999. And I'm not speaking German there. 9. No, right? I'm eventually going to be adding a bunch of 1s forever. So I don't realize that, and then I go to my partial sums, right? So I go to my partial sums. The first one's 1/2. The second one is what? 1/2 plus 2/3. Help me out there. What is that? 5/6. And then my next one is 5/6 plus 3/4, right? So what is that? 10, 19. Help me. I need an LCD of 12, right? Oh, I made a mistake on the first one, didn't I?
7/6.
7/6. Oh, look at this. 7/6. What's the next one? I need what? 15 and... No, 10 and 9, right? 19/12. Look at where these sums are going. Look at where these partial sums are going, right? They're getting bigger as I'm doing the sum. It's getting bigger and bigger. So I kind of, and then I'm trying to get a partial sum here. I'm trying to get my nth partial sum. I can't really see a pattern. What would be next? 4/5. So what would be S sub 4? It would be 19/12. Did I do the 19/12 right? Please, somebody help me. I did the 19/12.
24, I think.
What'd you get? What'd you get, Naima? For S sub 3, did you get something different?
24/12. So that's going to be reduced to...
Oh, so let me double check. So I want a 12 here, so I need a 2 and a 2. And I need a 3 and a 3.
Yeah, 38/24.
Oh, the next one.
No, that one.
Yeah, 38/24 is 19/12. I just reduced, right?
But the 5/6 should have been 7/6, I think.
I want a 12 downstairs, right? So I'm multiplying by 2.
The 1/2 plus 2/3 is 7/6. So the S of 3 is 7/6.
Does everyone agree I need an LCD of 12?
Yes.
Okay. So I need to multiply the first one by 1 in the form of 2/2. So that's 10 over 12. And the second one...
I think it should be 7 over 6, not 5 over 6.
Oh, that's what you're saying to me. I'm a dummy. I'm sorry, Nema. I didn't realize it. I'm blind to mistakes. 14 over 12 plus 9 over 12. Thank you. You were right. 23 over 12. Anyway, I don't see a pattern. I don't see a pattern here. I could work on the next one too, but I don't see a pattern. But so that's kind of so. But if you can test for divergence first, it will save you a little bit of time. So what do we want to do? We want to test for divergence, and that is look at the limit as n goes to infinity of n over n plus 1. That's a nice slopey tall, right? Derivative of the top is 1. Derivative of downstairs is 1, right? So I'm looking at the limit as n goes to infinity of 1 over 1, which is 1. Eventually, I'm going to be adding 1s, right? As I get all the way to the infinite term, it's really, really close to 1. I might as well be adding 1. And I'm going to keep going for another infinite number of terms. So I'm going to get divergence. So the series from n equals 1 to infinity of n over n plus 1 diverges. Don't put yourself through all that hell if you don't recognize it as something geometric or telescoping. Okay?
Professor, can you zoom out, please? I take a screen cap.
Yes. There's the whole page right there. It starts with tests for divergence at the top. I don't know if you can see it.
Thank you.
You got it. All right, one more thing to do today. So maybe 15 more minutes. I know what you're going through, so just try and do the examples in the book, and then try and do the problems I gave you on WebAssign. But this is the first one where you're going to kind of have something like this on the test. Okay. So we're going to create a power series. So our goal in 8.6 is to be able to create a power series using our model for power series, and then verify a radius of convergence using a ratio test. So I'm waiting on the ratio test. Okay. So the first thing we want to do is remind ourselves of that power series. So we had the series from n equals 0 to infinity of x to the n, which was 1 plus x squared plus x, etc. And we saw that turn into 1 over 1 minus x, and with a radius of convergence of less than 1. This is our model, and if you remember how I rewrote it by adding in the parenthesis for every x piece. So I'm going to rewrite it again. I don't care if you do or not. I want the x in parens. I want the x in parens. I want the x in parens. And I want the x in parens. And so what I have to do is figure out what I put into x, right? Figure out how I change my input, and then use the second box here, right? The blue box is my original one. The green box is how I'd like to create my new series. So I'm just comparing the two, right? So for example, if I gave you f of x equals 1 over 1 plus x, and I said to you, find me the power series. So if f of x equals 1 over 1 plus x, find the power series. Now, we have no problem integrating this, right? We have no problem integrating this as it is, but we're going to have a problem in a second, right? When I do the next example. So that's what we're trying to start with something that we don't need to do this with, and then we'll be able to do it with something that we must do it with. We do this all the time in math, right? So now I'm looking at what did I give you? I gave you this piece which is matching to here. So that's where I'm starting. If I'm giving you something that's matching the series part, or the term by term part, or that function notation part, that's where I want to start. So I want to start with 1 over 1 plus x is going to be equal to 1 over 1 minus something. And now what do you think I'm putting in there?
Negative x.
Yes, exactly. And so now you see I have that negative x in the parens everywhere in my model, right? In that green box above. Everywhere there's an empty paren, I'm putting in the negative x. So I'm now saying that this is the series from n equals 0 to infinity of negative x to the n. And I'd like to manipulate this a little bit before I do anything else, right? So I'd like to take care of the plus minus, the signs, the SIGNs, the coefficients, like if I had a 2, and then the x terms. I'd like the x terms to stand alone all the time. So this is now the sum of n equals 0 to infinity of negative 1 to the n times x to the n. And there it is. I've got my coefficients, or my signs, they happen to be the same. All my coefficients are plus or minus 1s, right? And my x terms, x to the n. And so now I can start writing this out. Well, let's think about it. When n is 0, that's an even power of negatives is going to give me a positive. So I'm going to get 1 minus x plus x squared minus x cubed, etc. Right? Do you agree with that? And this will connect back later. For my radius of convergence, I want to look at the absolute value of negative x is less than 1. What does the absolute value do? It kills that negative, right? So I'm back to my radius is 1. And this part will make more sense Monday when I do the ratio tests. I want to give you something substantial to work on over the weekend to be able to create power series, to be able to create Maclaurin series, to be able to integrate them. Okay, one last problem. I promise. I may have broken a promise or two already, but I promise this is it for today. I'm going to be around till 1:30, right? Feel free just to drop in. Just so you know, I'm probably going to make breakfast after this. So if I hear the ding, I will come in. It takes me, I live in a small apartment, so it doesn't take me long. But just be patient with me if you come in. Right, if you want to just stick around right after class, that's fine today, right? If you want to talk to me about anything, that's fine. If you want to talk in private, just tell me that, and that's fine, and I don't mind. I just create a little side room breakout room or something, and then we can talk, right? All right, let's see what we can do. Let's do an easy one of the more difficult. What? I want to create a power series for an ln function. So let's find a power series. For let's say ln of let's make it easy, 1 plus x. Now remember what my function notation should look like. I want to at the end be able to say that f of x is some kind of 1 over 1 minus x. And I'm going, what? Right now it has nothing to do with it, right? Right now it doesn't look anything like it. So what can I do? Well, the first thought you're going to have in your mind, and one of the notes you're going to have on your formula sheet, is you're going to try and integrate or differentiate. You might have to integrate twice. You might have to differentiate twice. I'll never make you do more than that. I think a couple of problems in the book where you have to integrate 3 times. They first have you integrate once and then integrate twice, then you realize you have to integrate one more time to get there. So what can I do to this ln function to kind of make it look like, and let me call this g of x here. It doesn't matter. It's going to be the same function. They're going to be equal. One is in function notation. One is going to be in a series notation. So what can I do to ln of x function to get it to kind of look like my g of x function?
Is that derivate?
Right. Differentiate. Right. Differentiate, yes? Juan, is that what you said? Derivative, yes?
Yeah.
Yep, so f prime of x, for the ln, remember I need the derivative of the inside over the inside. So I need 1 over 1 plus x. Okay, now it looks like it. But I just did this one, didn't I? I just did this one, right? This was 1 over 1 minus a negative x. And for that, I got the series from n equals 0 to infinity of negative 1 to the n, x to the n. Is that true? Remind me. I think that's what I got, right?
Yes.
And I can write this out for sure, right? I can write this out. I think I got 1 minus x plus x squared minus x cubed, right, plus etc. So I've got a power series representation, but it's not for ln. It's for the derivative of the ln function. So what do I want to do to get back to my ln function? Right? What do I want to do to get back to my ln function? I want to now integrate. So in these problems, you're going to be thinking about differentiating once, twice, 3 times, and then going backward. So integrating. Or integrating once or twice and then going backward and then differentiating, right? So in this one, I differentiated to get to a power series lookalike. And now I have to integrate to get back to what I started with, right? So I know that this ln of 1 plus x is going to be the integral of my f prime of x dx, which is the integral of the series from n equals 0 to infinity of negative 1 to the n, x to the n, or the integral of 1 minus x plus x squared minus x cubed plus ... forever dx. How are we doing? How are we doing? Anybody? Anybody with me? Adam's with me. David is with me. Charlie is with me. Hao Shen is with me. Ash, Juan, nice. Nice. Eruz is with me. Beautiful. Name is with me. Charlene's with me. I think everybody's with me. I don't know if you're not. If you're not and you don't want to tell me, I understand that. But I am a dentist. And you did show up to my office today. And I like to use the drill. So if you don't tell me which tooth, I'm just going to start drilling anywhere I want. Right? All right. Now I'm going to integrate this in two ways and make sure they match up. So I'm going to integrate the series first. Right? So how do you think what do I get? I get the sum from n equals 0 to infinity of negative 1 to the n. Coefficients don't change when I integrate or differentiate. So that's why when I create the series, I want to isolate the x term. So I'm going to isolate my x term. So what do I get? How do I integrate in x to the n? What do I do with my power?
Add 1.
Add 1 and then divide with the new power. Right? Oh, and there's a dx here, sorry. I'd like to simplify this if I can. It doesn't really look like I can. Right? It doesn't really look like I can simplify it much at all. But I'm going to come back to it in a second. I want to work on my other integral first. Right? There's not much I can do to that. I'd rather have a simpler x, just to tell you. I'd rather have a simpler x, but I'm not going to touch it yet. I'm going to see what happens. Okay, what happens in my integral? What do I get? What's my first term going to be? I'm doing this integral now, right? So we're just going to integrate term by term. So what do I get first term?
X.
Yeah. Good. Minus x squared over 2 plus
X cubed.
X cubed over 3 minus
X fourth over 4.
over 4, and I can really see the pattern here pretty darn easy, right? I can manipulate this a little bit. X to the 1 over 1. Eventually, I'm going to get to x to the n over n, right? Yes, you with me? And now I want to write the series for that, right? So it looks like I'm starting at 1, and that's fine. So n equals 1 to infinity. And I definitely need an x to the n over n. That's a little bit nicer than n plus 1 over n plus 1. And then what about my positive negative? How can I write the positive negative? Well, I want the first term to be positive, but the nth term is odd, right? So I've got to manipulate that, and the nicest way to do that is a negative 1 to the n plus 1. And that's my series, and I just want to double check, are they the same? Well, so how do you double check that they're the same? You write out the terms. So I've already got the terms written out for this, right? These are my terms. So I just want to write out the terms for this one, right? And see if they match up. And it's pretty obvious that they do. When n is 0, I get a positive, and I get an x to the 0 plus 1 over 0 plus 1. When x is 1, I get a negative, and I get an x to the 1 plus 1 over 1 plus 1. And yes, I can already see that they're matching up. And it's perfectly fine for you to do these both ways. I think it's easier just to do the series and then to rewrite the series with the simplest exponent for x as you can. So if you start n at 0, right, you need an n plus 1. But if you start n at 1, you just need an n, right? And so you're just going to manipulate the series. And it's easy to do that term by term at first until you realize what's happening. Okay. So you're doing examples in the book in 8.1 and 8.2. You have a homework done for 8.1. I will do a homework today for you for 8.2. You can start to look at my power series problems on old final exams, ignoring the ratio test bit. Okay, ignore the ratio test bit. Oh, by the way, well, if I did this now, if I did this particular piece here, what would be my radius of convergence? I can get integrating or differentiating is not going to change my radius of convergence. So I'm still going to have this minus x is less than 1, so r is 1, right? So, but I'll talk about that later. Don't worry about it. In the old test, it's going to say find the radius of convergence using the ratio test. Don't do that piece. Just create the power series. Okay. Heavy class today. Lots of material, lots of notation, lots of vocab. Lots of writing. But the power series part is more elegant. We just need these review sessions to be able to do the tests, to be able to come up with writing the series and that type of thing. But we're all done today. Oh my God, an hour.